Wonderful. Good evening. Today we're going to talk about quantum dots in noise-resistant quantum key distribution systems. My name is Prahlad Saravanapriyan.
My name is Praneel Samall.
My name is Aditya Das.
My name is Elaine Huang.
My name is Samuel Lee.
My name is Dhanya Ganesh.
My name is Ezana Makonnen.
My name is Sophia.
All right, so initially discovered in 1980, quantum dots are semiconducting nanoscale particles measured between 2 and 10 nanometers, or 10 to 50 atoms in diameter. Some materials of which they can be composed are cadmium selenide, lead sulfide, indium phosphide, zinc sulfide, copper indium sulfide, zinc sulfide, indium gallium arsenide, silicon, germanium, and carbon. They exhibit unique electronic characteristics that range from those of larger semiconducting materials and individual molecules. This is due to their exceptionally high surface-to-volume ratios, which manifest in fluorescence. Quantum dots generate colors based on their particular size, and this is made possible by the semiconducting crystal's radii falling short of the exciton-Bohr radius, which is the average distance between an electron in the conduction band and the hole it creates in the valence band. Now, as pointed out by Pauli's exclusion principle, this leads to the quantization of energy levels. Due to the discrete energy levels of quantum dots, they are more akin to atoms than bulk materials. As crystal size reduces, the energy gap between the highest valence band and the lowest conduction band widens. Quantum dots can also be classified based on their structure and composition into core type, core cell, and alloyed quantum dots. Overall, quantum dots have various applications due to the various benefits their distinctive properties offer. These include their optical abilities to emit pure, bright colors, extended lifetimes, high efficiency, and having a high extinction coefficient. Additionally, quantum dots, being zero-dimensional entities, exhibit a more defined density of states compared to structures with higher dimensions. An electron's travel distance is also reduced compared to larger particles, thereby enabling electronic devices to function at higher speeds. Quantum dots also possess size-tunable emission, high photostability, and narrow emission spectra. Quantum dots can be utilized in quantum computing due to their ability to function to their functional similarity to transistors. Information is not stored using transistors as in classical computers, but rather through individual atoms, ions, electrons, or photons that are entangled to form quantum bits, known as qubits. And these quantum scale units can hold multiple values simultaneously and process various tasks concurrently. Managing individual atoms and similar entities in this manner can be challenging, but utilizing quantum dots on a larger scale would simplify the process significantly.
What is QKD? QKD systems have the potential to revolutionize the way we communicate and protect our data. The development of new and more secure QKD systems, which could significantly impact various industries, including telecommunications, finance, and national security. Typical public-private key cryptography is a method along with a protocol that allows one person to transmit encrypted data to another person for them to read. A private key encrypts the data. If you want to make it clear that data comes from you, use a public key to send it out into the world, and then it can be decrypted. However, if you want to designate data for only one person, encrypt it with a private key, then your public key, and the receiver will decrypt it with a private key and his public key. Public-private key cryptography has used cases in various realms other than sending confidential information. For example, you can sign a document with your private key, and someone who has your public key can determine that you are the individual who signed the document. Quantum key distribution, QKD for short, is a cryptographic protocol that allows two parties to share a secret key over an insecure channel. However, QKD is based on the principles of quantum mechanics, harvesting the benefit of being unbreakable by current technology. A QKD system uses quantum entanglement and superposition of qubits to ensure a safe transfer of encryption keys for later communication. Existing platforms implement quantum-resistant algorithms which rely on mathematical complexity to ensure security. These algorithms, integrated into cryptographic protocols, play a crucial role in guaranteeing the confidentiality, integrity, and authentication of transmissions. They are designed to withstand potential threats from future quantum computers. It is also designed to be able to detect the presence of an eavesdropper. In an open data channel, you cannot detect an eavesdropper, but in QKD, an eavesdropper must disturb wavelengths, which can easily be detected.
Applications of QKD. QKD can be used for secure communications, financial services, government and defense, healthcare and medical research, critical infrastructure protection, and quantum internet. The quantum internet is a network of quantum computers that will someday send, compute, and receive information encoding quantum states. Limitation of current QKD systems. Single photon emitting laser diodes and photodiode detectors, which most QKD systems use, are sensitive to noise, which refers to the multiple factors that affect the accuracy of the calculation a quantum computer performs, including environmental factors such as temperature and background radiation. Quantum dots are a promising candidate for noise-resistant QKD systems. Their unique optical and electronic properties make them well-suited for QKD. For example, quantum dots can be used to generate and detect single photons, which are the basic unit of information in QKD. They can also be used to create entangled photons, which can be used to establish a shared secret key between two parties. However, QKD systems are still susceptible to noise. Noise can be caused by a variety of factors, such as environmental factors, electronic noise, and malicious attacks. Noise can degrade the security of a QKD system and make it easier for attack to eavesdrop on the secret key.
Description of project. Quantum key distribution systems hold the potential for secure communication by leveraging the laws of quantum mechanics. However, challenges arising from noise and environmental interactions can compromise the security and efficiency of quantum key distribution systems. This research aims to explore the theoretical aspects of utilizing quantum dots within noise-resistant QKD systems by leveraging advanced simulation techniques on a high-performance computing cluster. We will investigate the impact of quantum dots on enhancing the security and reliability of QKD systems. We have three models: quantum key distribution model, quantum dots model, and noise model, which models spin and charge noise. We are currently using these models in tandem in the integration process. More on that later.
The first step in our project was to implement the standard QKD with code using the IBM Qiskit Python library. We modeled individual photons sent between the two parties as qubits, and we were able to model photon superposition and entanglement using the Hadamard and CNOT quantum gates. To ensure that our basic quantum key distribution scheme functions, we simulated the scheme with and without the presence of an eavesdropper. We were able to successfully determine the presence of an eavesdropper during the simulation, confirming the validity of our simulation.
Next is the quantum dot model. So there are four main points for this model. First is simulating quantum dots in the QKD system. We use a variational form function to create a quantum circuit representing two quantum dots in a QKD system. This circuit, using rotation gates and parameterize, allows us to explore different configurations. The number of qubits in the circuit corresponds to the quantum dots in our simulated QKD scenario. The quantum circuit, governed by rotation gates and dynamic parameters, as I said before, serves as a computational canvas for our simulated quantum dots. Adjusting these parameters reveals various configurations, making it possible to explore the behavior and stability of quantum dots within the QKD system. Next is implementing quantum dot Hamiltonian parameters. So the polydict dictionary holds poly operators, and these basically act as observables for quantum dot interactions within the system. These operators define the characteristics of quantum dots, and it encapsulates the system's features. The Hamiltonian sums up the characteristics observed by poly operators, providing a roadmap for understanding the quantum dot system as a whole. This mathematical representation is crucial for analyzing the impact of different quantum dot setups on the stability and the reliability of the QKD system. Next slide, please. So the third important point is exploring quantum dot behavior. So we use the VQE, otherwise known as the variational quantum eigensolver algorithm, to explore quantum dot behavior within the QKD system. VQE adjusts variational parameters to simulate different scenarios, seeking the ground state energy of the quantum system. Optimal parameters obtained from VQE guide the quantum dots into stable configurations. The ground state energy indicates the stability of these configurations, with lower energy levels signifying more stable arrangements and resilience against external disturbances. And last but not least is the contributions to QKD security and reliability. Optimal parameters from VQE enhance the stability and the resilience of the QKD system. These parameters guide the action of quantum dots, setting up stable arrangements and improving the system's reliability and security. So basically, understanding variations in this ground state energy helps us optimize quantum dot performance. And targeting configurations associated with lower energy states makes the QKD system more secure and reliable, which is basically the ultimate goal of this model.
The purpose of a noise model is to explore sources of noise. These include charge noise, environmental noise, background radiation, and others. We do this in order to identify how they affect QKD systems. For the purpose of our research, we used the Qiskit AER library to create a model that explores both spin and charge noise. With our noise model, we also aim to figure out potential strategies to help mitigate this noise. In physics, spin refers to the angular momentum quantity associated with subatomic particles or nuclei. These are measured in units of the Dirac h, also known as h-bar, which is defined as the Planck constant divided by 2 pi. The spin values for electrons, neutrons, and protons are multiples of 0.5, while pions have a spin value of 0. The total angular momentum of more complex nuclei is the combined result of the orbital angular momenta of the constituent nucleons. Nuclei with an even mass number always exhibit integer spin multiples, while those with an odd mass number have half-integer spin multiples. Ground states of nuclei with an even number of neutrons and protons always possess a spin value of 0. There are random fluctuations in the spin orientation of electrons in a quantum dot. In the context of quantum computing, quantum dots are used as potential qubits, and so these fluctuations can affect the reliability of quantum operations. Pauli errors are common errors in quantum computing that can arise from various sources. These include imperfect gates, environmental interactions, or other noise mechanisms. This is the way in which spin noise is represented in our model. Most notably, the error rate associated with spin noise is tied to temperature variations. Next slide. In our noise model, we also represent charge noise. Charge noise is fluctuation in the amount of electrons in a quantum dot. These fluctuations often cause errors in quantum operations. In our noise model, the charge noise is represented using a stochastic matrix. We calculate the error rate based on the standard deviation of the charge from the mean. We also represent the effect of a magnetic field on the quantum dot in our model. We represent the magnetic field with a Hamiltonian, which is a mathematical operator that represents the total energy of a physical system. Our Hamiltonian here is time dependent, and so it's based on the cosine function to represent oscillations in energy. Next slide.
Current research. So starting off with single photon sources, quantum dots can act as efficient and high quality single photon sources, which are crucial for QKD systems. Researchers are exploring different types of quantum dots, such as self-assembled quantum dots and semiconductor nanowire quantum dots, to develop a robust single photon emitters with high photon purity and indistinguishability. Next, quantum dot qubits. Quantum dots can also serve as qubits, the basic building blocks of quantum computers. Researchers are investigating the integration of qubits based on quantum dots into QKD systems to enhance the security and efficiency of key distribution. This research aims to exploit the unique properties of quantum dots, such as long coherence times and ease of control, to improve the performance of QKD protocols. Next, noise-resistant protocols. Quantum dots offer the potential to mitigate various noise sources that can compromise the security of QKD systems. For instance, researchers are developing protocols that can tolerate high levels of noise and loss, such as the use of quantum error correction codes and decoy state protocols. These approaches aim to make QKD systems based on quantum dots more resilient to practical limitations and environmental disturbances. Finally, integration with other technologies. To enable practical deployment of QKD systems, researchers are working on integrating quantum dots with other technologies. For example, quantum dots can be integrated with photonic integrated circuits, allowing for miniaturization and scalability of QKD systems. Integration with on-chip photon detectors and quantum memories is also being explored to create compact and efficient QKD platforms. Integrated models diagram. In our integrated quantum communication system, we start with the quantum dot source. At this initial stage, we generate entangled photon pairs using quantum dots, which are semiconductor nanostructures with discrete energy levels. The quantum dots are precisely engineered to emit pairs of photons that are quantum mechanically entangled, meaning their quantum states are interconnected regardless of the distance separating them. We also define specific quantum dot parameters, such as the energy levels and the emission wavelength, to ensure optimal performance and compatibility with the rest of the system. Next, these entangled photons move on to the photon emission phase. Here, the photons are transmitted through a communication channel. During this phase, quantum gates and encoding schemes are applied to encode the information into the photons. Quantum gates are fundamental operations that manipulate the quantum states of the photons, enabling the encoding of secure information. This step is crucial as it prepares the photons for secure transmission over potentially insecure channels. As the photons travel through the communication channel, they encounter various forms of noise introduction. This stage accounts for the environmental noise that can affect the quantum states of the photons. Several factors contribute to this noise, including charge fluctuations within the material, interactions with phonons, which are quantized sound waves within the material, and other decoherence processes that can disrupt the quantum states. These environmental factors can introduce errors and reduce the fidelity of the transmitted information. Despite these challenges, the photons eventually reach the receiver measurement stage. Here, specialized detectors measure the quantum states of the incoming photons. This measurement is critical as it allows the receiver to decode the information encoded in the photon states during transmission. The accuracy and efficiency of these measurements are vital for the integrity of the communication. Following the measurement, the system moves on to the key generation phase. During this stage, the shared secret key is established between the communicating parties. The key generation process involves calculating the secret key rate, which is a measure of how many secure bits can be extracted per transmission, and the fidelity, which indicates the quality of the transmitted key. High fidelity is essential to ensure that the key is free from errors and eavesdropping attempts. To further enhance the security of the communication, we implement error correction and privacy amplification. Error correction involves applying codes that can detect correct errors that may have occurred during transmission due to noise. Privacy amplification techniques are used to reduce any partial information an eavesdropper might have gained, thus ensuring the key remains confidential. These techniques are critical for maintaining the integrity and security of the quantum key distribution. So finally, the process concludes at the end stage. So by integrating quantum dot technology for generating entangled photons, quantum key distribution protocols, and effective noise management and correction techniques, we're able to achieve a secure and reliable quantum communication system.
Our future goals include to develop accurate theoretical models of the QKD systems with quantum dots, and to analyze effects and advantages of parameters such as quantum dot size and error correction codes within the model. Based on our modeling, we aim to design new QKD systems that are noise resistant for the most secure and accurate systems with long distance capabilities that can be applied in a real world scenario.
These are all the sources we used.
A special thanks to ASDRP and Dr. McMahon. Any questions?